Now, in the preceding talk, you may have noticed that when we calculated this number of hours we spend on the subway coming to class this semester, that at the conclusion of our calculations, after arranging all of our conversion factors, multiplying and dividing appropriately, checking our units, at the very end, I rounded our final answer from a very exact 21.33 repeating hours to a much more round, uh, uh, much more imprecise 20 hours. We should note that in performing that calculation, one of our conversion factors, which we estimated the time it takes to go from my house to campus, is about 40 minutes per trip. And we recognize that this was something we measured. It was really an estimate that says the real number, the real value, lies somewhere between 30 to 50 minutes. 40 minutes is sort of an average estimate. And this is something we measure that carries this degree of uncertainty. One way we may say is that we think that the amount of time per trip is 40 minutes plus or minus 10 minutes. There's a range of values, again, this degree of uncertainty. In comparison, we use other conversion factors that were much more exact, much more, or that didn't have that same degree of uncertainty. We know that there's exactly 16 weeks per semester, and we also know by definition that there's exactly 60 minutes per hour. So two different types of conversion factors, things we measure that have uncertainty versus things that are more exact, things that we have counted that or might be a definition. Since our measured conversion factor, 40 minutes per trip, is not terribly precise, there's kind of a large range of 30 to 50 minutes, we can really only round our final answer to a similarly imprecise range, 20 hours as opposed to saying 21.33 hours. Because our conversion factor, our estimate of the length of this trip, wasn't very precise, it would be misleading to pretend that our final answer is more precise than that. It'd be misleading and a bit unethical to say we know it's exactly 21.33 hours per semester. In science and engineering, we have to be very, very careful about not over or underestimating how precise our final answer is, how confident we are in the value we calculated. We always need to represent our work truthfully and faithfully. To keep track of this measurement of precision, sort of the uncertainty associated with each of our measurements, we need to consider this thing called significant digits. You may also see it called significant figures. Significant digits, or significant figures, is a measurement of precision, and it reflects the idea that every tool we use, every measurement that we make, has some level of uncertainty or some error associated with it. We often represent the idea of precision with this sort of target and scatter shot look. We see that along the x-axis we have increasing precision, and looking at the two targets on the left, we see two targets on the left that are very imprecise, low precision. We see the spread of each shot aimed at this target is pretty wide. It's all over the place, not clustered very tightly together. In contrast, the ones on the right tells us a more or contains a more precise shot. We see that all the shots aimed at this target are clustered very closely together, which is a very precise shooter in this case, and has a very small level of error, small level of uncertainty, clustered tightly together. This precision of a measurement tells us between which values our measurement falls in. There's a difference between saying I know my trip lasts 40 minutes plus or minus 10 minutes versus saying I know my trip lasts 40 minutes plus or minus 1 minute or 40 minutes plus or minus 1 second if we're ultra precise. The higher the precision, the smaller the range of these potential values. One thing we need to be careful about is not to confuse precision with accuracy. We can see in the same chart that accuracy is a measurement of how close to the true value we are. We see that the top two graphs, which are very accurate, are all centered at the center of this target, at the center of this bullseye, compared to the two on the bottom are much more spread out. We can have measurements that are precise but not accurate, as we see in the bottom right, in which they're clustered very closely together, but far away from the center of the target, far away from the true value of our measurement. We can also have things that are very accurate but not precise, as we see in the top left. Again, they're all centered around the middle of the target. On average, they tell you the true value, but the spread and uncertainty is quite large. Let's do an example of a way we would measure and produce precision and significant digits. Consider this fish. Let's say we want to measure how long this fish was. If we were to use a top ruler, we can see that this top ruler only has lines every 10 centimeters, and because it has fewer tick marks, is less precise. We can only confidently say that this fish is somewhere between 50 to 60 centimeters. In comparison, the bottom ruler is more precise. It has more tick marks, and we can see that the end of this fish lies somewhere between the tick mark denoting 53 centimeters and 54 centimeters. In order to communicate which ruler we used, how precise our measurement was, and how small or large the error is, we need to keep track of significant digits. We need to record the data in a way that communicates how many tick marks this ruler had. Our standard convention that we use within science and engineering is that when we use a tool like a ruler, we record the measured digits. So we count the number of tick marks, and then we add one more estimated digit, which estimates the distance between those tick marks. So for example, using the ruler up top, we see that the fish falls between 50 and 60 centimeters. And we're going to estimate that's about 3/10 of the way between 50 and 60. So we'll record it as 53, including this one estimated digit, which is the 3. And by contrast, the more precise ruler at the bottom, we see and can count 53 tick marks. So we write 53. And we estimate that the fish falls halfway between 53 and 54. So we're going to record 53.5. More significant digits typically indicates a higher level of precision, more closely or smaller tick marks, a lower uncertainty or lower error in that measurement. Important to note that even if the measurement falls exactly on a tick mark, and we would estimate the final digit to be a 0, we should still record that 0 because, again, it keeps track of the precision of this tool. Let's do another example. Let's take a look at this thermometer. In the case of this thermometer, we see that the mercury level falls between the line denoting 76 and 77. So we would record 76 and estimate one more digit, 76.5 degrees Celsius. If I were to just record 76, if I got lazy and I didn't want to write all the digits down, it would communicate to other engineers that my thermometer wasn't very precise, that I only had markings at 70 degrees and 80 degrees, and I'm estimating the distance between 70 and 80. So again, we need to record things correctly so as to communicate how precise our tools are. If we use a digital tool, one that displays a number for us, such as a laboratory scale, most of the times the estimated digit, the error, will be reported for us. So you might use a mass balance or a scale with a digital display that'll show you the weight as 2.334 grams, and you would see somewhere next to that label would be a precision indication that says plus or minus 0.001 grams. When we use these types of digital tools, which may be calipers, might be a scale, might be some other sensor, we can interpret that this last digit displayed is the tool estimating the digit for us. We still estimate that it means that if we measure 2.334 grams, this imprecision of 0.001 grams means that the real value, if we were to measure this and repeat the measurement 100 times, would lie somewhere between 2.33 grams and 2.335. Again, every tool is imperfect. If we measure something more than once, we may get slightly different answers, all related to the imprecision or precision of that tool. Now, significant digits, again, are a way that we interpret if someone makes a measurement, how precise their tool was, and how precise or how confident they are in that number. Let's say that you're a doctor or you are working with a doctor who weighs your baby and they want to determine the appropriate dose of a drug. Very important to know exactly how much that baby weighs so you don't over or underdose that baby. If the doctor is quite lazy and only reports it as 10 pounds without indicating significant digits, we're not sure of the error or uncertainty of that weight. When we think about it, if you were to write 10 pounds, that might indicate that the baby is somewhere between 9 to 11 pounds. If we were to write 10.0 pounds, it might indicate a weight between 9.9 to 10.1 pounds. But there is a scenario in which we use a very imprecise scale that really is estimating this 1 in the tens place, and that really we're only confident that the baby is somewhere between 0 through 20 pounds. Our significant digit tells us which digit is estimated, which one we are the least confident in, and what the range of potential values might be. We should all use significant digits because it's how we not just make measurements, but make measurements that are useful and reliable. Now, when we're given numbers or we see numbers presented to us, we can determine how many significant digits that number has just by looking at it, and of course then interpret how precise that tool was. If you see a measurement of some sort of unit, you can know that all the non-zeros, all the digits that are 1 through 9 are a significant digit, something that was measured or estimated. The hardest part is to know when there is a 0 present in a number, of whether that's a significant digit. Sometimes a digit or sometimes a 0 is only there from a unit conversion. It's just there as sort of a placeholder representing very small or large numbers. If I were to measure 1 gram, which has one significant figure, a very imprecise measurement of mass, representing that same mass in kilograms as 0.001 kilogram, these zeros don't magically make the 1 gram measurement more precise, and so these zeros we consider as not significant. They're not something we measured or something that was estimated. They are there simply as a placeholder as a result of a unit conversion. Of course, there are many instances, as we see when we measure tools that the fish falls exactly on the line, for example, that a 0 can represent an estimated digit at the end of a measurement, in which case that 0 is indeed significant. Measuring 10.0 pounds on digital scales means that this 0.0 is being estimated, and the real weight is somewhere between 9.9 and 10.1 pounds. That 0 at the very end is a very important 0, a very significant 0, that tells us the precision of that scale. Generally, we see that the more significant digits there are, the smaller this percent error will be. So we typically look for more precise numbers with more significant digits. When we see zeros, we sort of have an algorithmic way to determine whether or not this 0 is a significant digit. Our two rules for zeros are, if a 0 appears between non-zeros or at the end of a number with a decimal point present, that is a significant 0, something that is measured or counted. If the zeros are at the beginning of a number or at the end of a number without a decimal point, they are not significant, they're just as a placeholder. Let's look at some examples so that we can get our heads around this rule. If we see 3.02, the 3 significant, the 2 significant, and the 0 between the non-zeros are significant. So this number has 3 significant digits. You can sometimes write it as sigdigs, depending if you're cool or not. Similarly, if you see 5,280 decimal or 5,280 dot, this 0 at the end of a number with a decimal point is significant, something that was measured, in this case estimated, giving us 4 significant digits. And by contrast, 0.05 only has 1 significant digit because it's at the beginning of a number. 0.0500, 3 significant digits. The 2 zeros before the 5, not significant. The 2 zeros after the 5 with a decimal point are significant. Oftentimes when we record large numbers, such as if we were to write 200, we have to be careful to represent the significant digits appropriately. If I were to just write 200, let's say I wrote 200 milliliters or 200 pounds, Without a decimal point, I'm communicating that those two zeros are not significant. There's only one digit that's significant, only one digit that's measured or estimated. That is a different situation, of course, if I was to write 200 point or 200.0, in which those zeros after the 2 with a decimal point indicate significant digits. Why are we so persnickety about these significant digits? Why does this precision matter? Quite often in science and engineering, we need to extrapolate from a measurement, and sometimes that turns into a very, very big or small number. By doing these calculations, the error does get magnified, and we need to make sure that we communicate appropriately the uncertainty with any measurement and any calculation that we make, particularly as engineers, people who are outward facing, who interact with the public. The results of our calculations have a lot of effect on people's lives, well-being, livelihood, safety. Arbitrarily trying to make our number look more or less precise by rounding these numbers just willy-nilly is quite dangerous and quite unethical. We cannot pretend our work is more precise or less precise than it really is. And so in order to make sure that we're communicating not just the precision and uncertainty of the measurement, but the precision and uncertainty of our calculated values, we need to follow some rules to preserve that significant digit. When we take numbers and we add or subtract them, the rule is that we perform normally the algebraic operation with all our digits. We keep every bit of the number, and then we round to the least precise digit. By example, let's say we took 1.26 milliliters and we added 2.2 milliliters, two different volume measurements with different levels of precision. We see that 1.26 milliliters has a significant digit out to the second decimal place, while the less precise measurement, 2.2 milliliters, only has a significant digit out to the first decimal place. To perform this calculation, we would plug numbers in as is to our calculator. We get 3.46 milliliters, but then we would need to round this final number to represent that 2.2 milliliters wasn't a very precise measurement, only has a precision out to the first decimal place, and so we would round this number out to the same precision as the least precise digit, the first decimal place in this case, giving us 3.5 milliliters. Another example, let's say we took 1,200 grams and added 10.3 grams, different levels of precision. Here we note that 1,200 grams without a decimal point only has a significant digit out to the hundreds place, out to this 2. When we do this calculation, we'll get 1,210.3 grams, but we have to round it out to the hundreds place, which turns back into 1,200 grams. Now this is going to look weird, and this may be a little counterintuitive, but if you think about it for a second, by measuring 1,200 grams, our imprecision says that our actual measurement, the uncertainty, is anywhere between 1,100 to 1,300 grams. Such a large range of error, such a large range of uncertainty, means that adding a very, very precise but very small 10.3 grams doesn't actually change that number all that much. The error is still within this wide range of 1,100 to 1,300 grams, and so our final answer is still within that range of 1,200 grams with two significant digits out to the hundreds place. When we multiply and divide things, we have a different rule. First, again, we perform the calculation with all the digits. We plug everything into our calculator, but then we round to the fewest total number of significant digits. So if we took 2.3 grams and divided by 1.224 milliliters, we get 1.879 something something something, more decimal places beyond that, grams per milliliter, a measurement of density perhaps. Because our 2.3 grams only has two significant digits, we round our final answer also to two significant digits, in this case 1.9 grams per milliliter. Same thing we would see here with 10.2 grams divided by 5.1. Again, two significant digits limited by the least precise measurement with the fewest number of significant digits. Like when we make measurements, if there's a 0 as a result of rounding, we keep that 0 because it still tells us the precision of that calculation. We don't truncate it just to make it look cleaner. Should we need to do compound math, by which I mean we both add and subtract and multiply and divide, we want to make sure that we only round at the very end. If we round after each operation, after each step, we may get rounding errors, which will change our final answer. What it means practically is that we need to keep track of the significant digits after each operation, but only round at the very end. Here's an example. We have this compound operation. We subtract things and then divide them. In the first step, following normal order of operations, we subtract 7.225 grams minus 0.21 grams. We get 7.015 grams. Because 0.21 grams has a significant digit out to the second decimal place, normally we would round and truncate this number at the second decimal place. But because we have more to do, we don't do that yet. We simply make note that we would normally round here to the second decimal place to 3 significant digits. We then perform the operation using the full number, 7.015 divided by 7.2, and we get 0.9743 something grams per milliliter. Only here at the very end, recognizing that 0.97 grams per milliliter has 2 sig figs formally, we round it to two significant digits, 0.97 milliliters. Had I rounded earlier, had I rounded 7.015 to 7.02, I would have gotten a different answer, an incorrect answer from a rounding error. There are essentially 2 types of numbers you'll encounter in your calculations. First, we'll of course encounter measurements. These are things that have significant digits, things that we track the level of precision because they're made with some sort of tool. But you may also encounter what we tend to call exact numbers. These exact numbers are things that are counted, or things that might be a definition that ultimately have infinite precision and infinite significant digits. We can typically ignore exact numbers when we try to calculate how many significant digits our final answer has, or ignore significant digits when we figure out how to round the final answer. Looking back at the example we started this section with, we see that for this calculation of figuring out how many hours we spend on the TEA this semester, we can see we have 2 types of numbers. 1 semester, 16 weeks per semester, 1 day per week, 2 trips per day, and 60 minutes per hour are all exact numbers. They're things we count. There's no uncertainty associated with how many days there are per week or how many trips we make per day to get to and from class. The only measurement we make here is that we estimated that we take about 40 minutes per trip, but it's an estimate that has some uncertainty. We of course know that because this measurement is not terribly precise, with only 1 significant digit as we recorded it, our final answer can only also have 1 significant digit here because we have multiplied and divided everything. So we take our final 21.33 repeating hours, and we have to round that out to 20 hours with also only 1 significant digit. Again, we try to do so because we want to preserve the uncertainty, how confident or not confident we are in this 40 minutes, make sure that comes through and is translated through in our final answer.